organic fragments of some kind and make an impact mass spectrum of these, then what should we see? So essentially take this fertilized kind of idea and look for these fragments in space, in situ. Because that is what we have. So we have about 70 grain measurements now from this kind of thing. So from solar system measurements, looking into the dust thing entering the solar system, we have about 40 bands. So do you have any kind of comments on what kind of signatures? So really looking at this, say 100 nanometer size grains. No, we are looking at the grains. So these grains flying around in the solar system, coming in and hitting the plate, and we are smashing them to pieces and making mass spectrum of these grains. So we really look pretty similar to what you could do in laboratory. And now we are looking for the possibility of using some kind of laser acceleration techniques to accelerate in laboratory different kind of fragments to be able to simulate these kind of things, to build up. Essentially put some kind of spore or microorganism and then blow a laser at it, and then it evaporates part of it and the rest of it flies at 10 kilometers per second into the wall, and then you look at the fragments. What's best draft? This is Stardust, so we have actually just published in Science the first report.
But if you compare it with, for example, oil and gas talking about the equalized kind of a spectrum and this kind of a broadband spectrum.
No, I'm not talking about, because here you have only touched now the question of how to detect it by optical or different kind of electromagnetic waves. We are grabbing whatever fragments, the dust grains, IDPs. We grab them and then we analyze them directly in space, in situ. In situ, okay. In situ, yes.
What sort of instrument you use then? When are these recorded in the silicon flow, or are they?
Pardon?
How do you catch them? They're recorded in the silicon flow, right?
No, they are directly in place. So when we fly in space, we collect them. So we have a large relative velocity, typically 30 kilometers per second for these IDPs, and then when they hit silver plate in this case, then they are completely defragmented. So they are smashed into pieces, and we can get then the mass spectrum from these pieces, and these mass spectra show directly clearly that we have an overwhelming majority of organics in all of it. You see almost no kind of ordinary. They are all complex organic structures.
How do you know that it's silver and not silver? Is that usually where they come in?
So that is speculation. So the instrument is pointed just into this the direction where we know that the dust is mostly coming from. And so we have no proof, and also the dynamic is very complicated, so it's hard to say what this will be. So it's that is speculation, yes.
But the silicon field also collected some samples.
Yes, so the Stardust spacecraft has a bunch of instruments on it, and one of them is this, which does in situ measurements. And the other one is this aerogel cushion, which is about half a meter in diameter, 30 centimeters in diameter, and that will be brought back to Earth in 2006.
Yeah, it collected, I think it was that.
Yes, and that has collected IDPs on one side, and then on the other side it collects this cometary flyby stuff. And the problem is only this, that for these 30-40 kilometers per second speeds, it's hard to think that any of these grains on this interstellar dust would survive. So they would evaporate, and then we wouldn't see essentially anything. So this is the kind of thing. And my question simply here was that you have any kind of ideas about what kind of signatures one should look for. So what kind of structure, or do you know about any kind of programs?
So I don't know how exactly you can look for this kind of, suppose you say pyrimidines or something like that, some kind of that. pre-biotic thing. Is it possible to look for that particular thing in your in-situ measurements?
Probably, yes.
Because that is the kind of a thing which will give some kind of a idea that we do have a extraterrestrial, because the stardust definitely has to be extraterrestrial kind of thing. But, so if you are detecting the pre-biotic meanings, I mean, it really is that kind of, not just the ordinary organic compounds, but this kind of breakup of a living organism to because of impact it's going to whether such kind of things is possible. I don't know what is related to it, I don't have any idea.
Because one of these things we have reported actually also at the cross-participation is that we seem to have nitrogen in certain of these. One can see certain molecular groups in these mass spectra. And that means really that one should go in here and take a sensitive look at what kind of molecular structures would be essential for life form, and then this way turn this question upside down.
Shouldn't one look at the full aromatic hydrocarbons?
Yeah, that you can see.
Have you seen them? Because certain different groups, like some of them are more like.
Yeah, there is a whole bunch of these available. So there are typical triplets of different kinds. One can infer quite a lot about these structures.
Actually, the kind of hydrocarbons, pulsar aromatic hydrocarbons, doesn't really immediately tell you about the life, whether it can come from life or living cells, but it doesn't. Whereas if you are going to have a compound like this, it kind of some kind of compound like that. That would be, I think it will be able to survive the impact of 30 kilometers per second. That's what you said.
Yeah, it's typically that, and then the cometary fiber is much lower, so then we...
Okay, so that's why I felt that maybe we can go one step ahead. But just aromatic hydrocarbons, look for the higher form of the thing. That would be sort of the right step towards really, if you detect that, that means definitely there seems to be some kind of, isn't it true? I mean, this is just my guesswork with that.
Okay, so thanks very much, Andrew. We come now to the next talk by Gerda Horneck. She is from the Institute of Aerospace Medicine in Cologne. Please go ahead. We talked about astrobiology studies on microorganisms in outer space. So please.
I would like to thank the organizers for inviting me here and giving your talk about our studies, mainly in the Earth orbit, and maybe you'll find out that also some studies on the periodic evolution of organics could be done using this kind of facilities, and maybe we come up with some ideas also what can be done by using it. I'm proposing we will be using is actually the International Space Station. So mostly astronomers think this is just an empty cannon that cannot do very much with it. But I hope I can show you that it's also an interesting test for exposing different kinds of organics or microorganisms to selective parameters of the space environment. And actually the next exposure facility, which is built by ESA, will be attached to the Russian part of the space station, the Zvezda. It was originally planned to be attached to the European Columbus facility, but due to the Columbia accident, this is so much delayed, and we can now use the Russian platform first. And if the Japanese bring their module to the space station, then there is also a huge exposure palette which can be used. And there are different places, for instance, on the truss structure, which was first thought could be used. So the space station offers a huge platform where you can do studies. And the studies which we want to do on the first space station, I will come to it, but first have a look what are actually the parameters of the space environment which we can study on the space station. So, number one, it would be the space vacuum. And the space vacuum in free space, you have a very high, ultra-high vacuum in the range of 10 to the minus 14 Pascal. But in Earth orbit, where the space station is, that's by orders of magnitude a lower vacuum. It's in the range of 10 to the minus 5 to 10 to the minus 6 Pascal. And that has also been measured in the space shuttle. And because it's also outgassing, it's even less. So I think this is about the vacuum you can also easily simulate in the laboratory. Solar UV radiation is something special. The whole spectrum of solar UV radiation, extraterrestrial solar UV radiation, is very difficult to be simulated in the laboratory. Then we have, in addition, the galactic cosmic radiation, which consists of protons and heavier particles, helium particles, and 1% particles. Very heavy particles, heavy ions, and they are of special biological effectiveness. And then you have extreme temperatures, depending whether you are oriented to the sun or in the shadow. Microgravity might be of interest for some studies, for levitation studies or grain aggregation. And of course, we have to do such experiments for an extended period of time. We think that the space station will be at least there for 10 years or even more. So on the first, in the first series of experiments, there are 8 experiments have been selected, and 2 of them deal actually with pre-biotic chemistry. So they want to simulate the interstellar organic chemistry by using some primordial molecules and expose them to the very intense vacuum UV radiation in vacuum in space. Then also simulating conditions of the primitive Earth, where you have the full UVC and UVB radiation, and so to understand whether one of the hypotheses that the precursors of life were delivered to the Earth by micrometeorites is likely or to test it, or whether the organics were more produced on the primordial Earth, the precursors of life. The 2 investigators are André Brack and Pascal Ehrenfreund. The next book deals with the evolution, somehow studying the evolution, processes of the evolution of life on Earth, and especially the role of solar UV radiation on these processes, because you can have the spectrum applying to the organisms that is the same as of the early Earth. That means no ozone layer. And you can also study, for instance, what is the effect of the ozone layer by simulating different layers, thicknesses of the ozone layer. And we'll come to some experimental results which we have already obtained. Or you simulate some UV radiation climate of other planets, for instance of Mars. And here are the investigators, Charlie Bockel from British Antarctic Survey, John Cadet, who does photochemistry, and Giorgio Manto from the Hungarian Academy of Science. And the third group, where I'm also very much involved in, is to study whether it's possible that life can be distributed between the planets. We all know that the planets are not isolated. We have found meteorites that came from Moon and also from Mars here on Earth. So material can be exchanged between different planets. The question is now, can also organisms which perhaps are embedded in the rocks also survive such a journey? And there can be done some experiments in space, for instance, the survival of microorganisms in artificial meteorites and how well they can be protected by chemicals or by minerals, and so to study the chances and limits of interplanetary transfer of life. And I just today met one of my co-authors in the paper which discusses all this. That's And the first author is Dr. Lakowski, and he gathered a whole group of people around to discuss this question, and I met Marek Horneck today, and we have already several papers written together, just through electronic communication and so forth with Lakowski. So the authors, the experimenters are here, besides myself, Nobuo Nakata from Japan and Rocco Mancinelli from NASA or SETI Institute. Now I show you a little bit the facility. In my pictures here, it's always the one which is attached to the Columbus facility because it was the first plan. But actually this part is now free for new proposals because all the experiments will be done on the Russian module, and now, so it's very important if you're interested to do such kind of experiments, that there's a new AO from ESA where you can apply doing such kind of experiments. You see it's more or less like a pressure box, and it has different compartments, and the different compartments are either open to space, that means vented, or they are hermetically closed to the air, so you can keep whatever you want, some inert air, noble gases also inside, and then they are covered with different filters so that you can select the UV radiation you want to. Of course, there are also radiation dosimeters, and this one will then be brought to the attached to the outside by an extra-vehicular activity. Here this picture just shows how they attach the solar experiments to measure the solar irradiance, and at the same time we will have here our exobiological experiments, which is very interesting because the other group measures all the solar constants, the solar spectrum, and that is very nice information for us. So the first flight, as I said, will be on the Russian in next year. So we are very much at the moment in the preparatory phase, and the next one will be 2007, depending on the transport to the EIS by Columbus, but I think it will be in 2007. And so this is now open for new proposals, and then it will stay for 3 years in space. And of course, what's very important if you do space experiments, that you always have parallel ground control experiments. And here is a little bit further design. So we have more than 1,000 little compartments for biological and chemical samples, and they can then be somehow arranged in such a way that you can select the test parameters, what kind of the solar UV radiation spectrum. Galactic cosmic radiation is always there. There is no special shielding, space vacuum, temperature, and of course the time. So these are a few examples here. We use normally our bacterial endospores. These are our house bugs. We have tested them always because we have the feeling there is no other microorganism in the world that is resistant to this complex interaction of the different parameters of space. There are some which are more radiation resistant, like Microdinococcus radiodurans. There are some which are more heat resistant. But to the complex interplay of space environment, we think bacterial endospores are the best. Nowadays, one has also found them inside of basalt rock, so they are also endolithic. Another organism which is very interesting are those which are living inside of salt crystals, so osmophilic microorganisms, they will be tested, and also those which live inside and outside of rocks, lichens or cyanobacteria and biofilms, and they will also be part of this first set of experiments.
What species would you use there for the bacterial endospores?
The bacterial endospores are the satellites. Or Atrophaeus, but that's also the Solosatellis, it's just another name. We use colored ones that are pigmented and non-pigmented. This is Haloarcura, and here we use cyanobacteria, Prococcydiopsis, and lichens, Entocarpon, Geographicum, and Sartoria elegans. But of course, this is just for the first run, there can be others. So what is very important if you do this kind of space experiments, that you need to do a lot of what we call experiment verification tests before. Test whether you do the experiment and get the samples back, you have to prepare. Do they tolerate vacuum for a long time? Do they tolerate the temperature? So you have to know which kind of organism you really have to do put in the space experiment in a lot of preparatory studies, and this is one of our space simulation facilities. We have a total of 9 different ones where we can put a whole tray inside, and then we have here 8 different deuterium light sources for vacuum UV radiation. You can control the temperature and have, of course, vacuum inside. And then one has to do an experiment sequence test. We will do that at the end of this year, where you do everything like in rehearsal. You bring your samples to the central point, you mount them in the sample tray, and then you expose them to selected simulated parameters. We do it not for 3 years, but for 3 months. And you get the samples back, and so you do the whole process before you really do the right space experiment. And then you need to have, during the whole mission, a parallel ground control experiment in the laboratory, at least exposing them to vacuum and some selected UV radiation. And now I want to give you some results which we have obtained so far. One of the first ones was in the cargo bay of the space shuttle during the Spacelab 1 mission. And we had there a small tray which was at that time built by our DLR company itself. And here you see the little quartz plates, about 7 millimeter in diameter, where the bacterial spores were exposed to. And again, we had the parallel ground control experiment in the laboratory. And these are the results, or some of the results. We just wanted to know how do they survive in the solar ultraviolet radiation. Here you have the extraterrestrial spectrum, the terrestrial spectrum, and this is just a survival curve, so the survival rate as a function of the time of exposure. On Earth here, you have a different scale. This is 100 minutes, and in space this is 1 minute, so it's nearly a factor of 100. And what you can see that here in space, compared to the Earth, it's about a factor of 1,000. And what happened here? 10 seconds of exposure kill 90%, so 10 seconds would be about here. 10 seconds kill the spores by 2 orders of magnitude, and compared to 100 seconds, or no, I think it's about, we can say about that in space, the killing is 1,000 times more effective than on Earth. And that means that the original idea of panspermia, which Arrhenius had put forward, that single spores driven by the radiation pressure of the sun can be transported through the solar system, does not hold, because single spores are immediately killed by the very intense and high energetic UV radiation. Let's see, another experiment was done on the Eureka mission, also the European Retrievable Carrier, which stayed for 9 months in space, and for 6 months it was permanently oriented to the sun. So we had a very, very good long-time solar irradiation. Actually, this is an experiment which I don't report at the moment, but it was done by Mayo Greenberg with this yellow stuff, so pre-simulated substances of the chemical substances of the interstellar medium, and he calculated that the conditions which the solar UV radiation conditions would be comparable to about 10 to the 7 years in the interstellar medium, so for a very long time. So it's really a good experiment, and he found that with the data he could confirm his model of cyclic interstellar grain processes. What we did in this experiment, we used different short wavelength filters, irradiated the samples for defined times at different wavelengths, and did the same inactivation curves which I showed you before for the whole spectrum, and in order to determine what is the effectiveness of the different wavelength ranges. And what you can see is what we call an action spectrum. So the spectral activity and that especially here would the terrestrial spectrum start, so that you have an exponential increase in the inactivating efficiency within the short wavelength range. And what we also could find that if they were irradiated at atmospheric pressure or in argon, they were less sensitive than when they were irradiated in vacuum. And we studied also the photochemistry that is behind that. So, next experiment was on the role of the ozone layer in protecting our life on Earth, because we know in the early Earth had no ozone layer, and maybe what happens in the future, one does not know. So we studied and the D2 mission, again, in the cargo bay of the space shuttle. We had now an experiment which looked very similar to the one which I showed you before, but in this case we had not bacterial spores individually, but a so-called biofilm, which we normally prepare to measure. It's a biological UV dosimeter for measuring personal UV exposure and these things. And the intent, after exposure, we develop the film, we let the spores germinate and stain the living ones, and the intensity of the color gives you a direct measure of the biological effectiveness of that radiation. And so we used here different cut-off filters which simulate different thicknesses of the ozone layer, of the terrestrial ozone layer. This would be the current terrestrial ozone layer, and then in this, the ozone layer is decreasing. This is without any ozone, full spectrum. And here we then determine the biological effectiveness. This is a terrestrial experiment. Here you see again the ozone layer thickness decreasing from here to there, and you see an increase in the biological effective dose. And so, for instance, Dobson units of 100 we have already in Antarctica, and that's already an increase by a factor of 10. And from nowadays to no ozone, it would be an increase in the biological effectiveness of a factor of 1,000. So that is, with these very exact measurements, it's the same which we found before in the more global experiment. So extraterrestrial solar UV is 1,000 times more effective in killing spores than terrestrial. And this dotted line is actually a calculated line for DNA damage, and that fits very nicely with our measurements. And so the measurements confirm the model so far used. Then we were interested in an experiment on a quite other facility. What is the protective power? We know individual spores are immediately killed. So protective power by different kinds of substances. We use Mars regolith, we used different meteorite powder, even Martian meteorite powder, or a chemical glucose, because this is not used as a nutrient but as a sugar, and normally if cells dry out, sugar molecules can replace the water molecules and thereby stabilize the biomolecules. In this case, we used another facility which is now also offered by ESA. This is a Russian photon satellite, and there they have a so-called biopan attached to it, and when it's in orbit, then the lid opens and you have two exposure areas where you can also expose different material to the space environment, and that is only for 2 weeks in space, so you get your data quite quickly. And again, a simulation experiment needs to be done before and during the mission. And now I give you very quickly go through the results. We again looked for the survival of bacterial spores. In the first case, we had them just under a quartz disk. So everything above 200 nanometer of UV radiation could reach the spores, and they were in vacuum. They were all vented. And you see here the data results, and you see that the survival rate is very low. 10 to the minus 4 to 10 to the minus 3. We use different kinds of spores which have different repair capabilities. What you also see, what's very important, we had 4 different controls. The lab control, which we did immediately when we prepared the samples. A lab control, which was just kept in the shelf after we got the samples back. The ground control was kept during the time of the mission in vacuum and was then analyzed, and the flight unit dark, which was below this one, so it had all the flight effects, just no UV radiation. And I think that's very important if you do a space experiment, do as much controls as you can do. So if there was no protecting at all, only quartz, then we had a very low survival. And then we mixed them with these different materials which I showed you, Martian dust or glucose, and so they were at the same place but mixed with this material, and then you can see that the survival was increased by several orders of magnitude already, just by mixing them with this dust powder. And the third one is then we made little, what we call artificial meteorites, they are about 1 centimeter in diameter, little spheres, mixing bacterial spores with this dust, and what you can see that the survival rate is nearly the same in the controls, in the dark controls. So 1 centimeter of material, dust material, would be sufficient to protect them very efficiently against solar UV radiation. Of course, ionizing radiation is something else. And then for long-time exposure, we used the LDEF mission, the Long Duration Exposure Facility, which was for 6 years in space, and we had also bacterial spores there, and again, controls, and what you can see here, that those, they were protected against sunlight, just in vacuum. That those which were in thick layers and protected with some sugars, that we had after 6 years, still about 70% of the spores survived, whereas if they were in thin layers and not with no protective agents, we had still 1% survival. So that is quite high number. So much studies for the solar UV radiation, now studies for the effect of cosmic radiation, and you have a variety of different sources, mainly the galactic cosmic radiation is of special concern, and in order to study this, you need because they are not like an X-ray, also you have a heavy ion here, you have a heavy ion there. So in order to study the effects of these heavy ions of cosmic radiation, you need somehow to trace them back. So we developed a kind of what we call biostack. It's a stack of track detectors, and in between the biological layers. And by this you can then, after the space flight, disassemble and after development of the track in the detectors, you can identify the different biological objects hit. We did that during many space flights with very many different biological objects. Only the one which we used were the bacterial spores, which is especially difficult because the bacterial spore is just 1 micron in size, and you need microscopes to do that. But we did that, and we could then identify the inactivation, the chance of inactivation, or the percentage of inactivation of the spores as a function of the distance from the particle trajectory. So here, these cells were all hit in the heart, in the core, in the central part, and then you have a decrease, which is, so it shows that those that are centrally hit have a very high chance to be inactivated, but it's not 100%, it's in a range of 70%, and we could also confirm that at accelerator experiments. And then it extends further away. From this we could, at the frequency, for instance, of iron particles, we could calculate that there is a chance for a spore to escape such a heavy ion, an iron particle, during a time up to 1 million years. So, I come to some resume just from our experiments in space. Extrasolar UV kills 90% of bacterial spores within 10 seconds. Space vacuum increases the UV sensitivity of the spores, and it's also mutagenic, but in principle they survive quite well. And so for 6 years in space they could survive very well if protected against solar UV radiation. And a meteorite layer of more than 1 meter would increasingly protect the spores against galactic cosmic radiation. This is a result of this study that was done by Kurt Milavkovsky and his group. and they can escape heat by a cosmic ion particle for up to 1 year. So one should, with these data, try to revisit the hypothesis of panspermia. And we can conclude transport of microbes inside rocks through the solar system appears to be a feasible process, and especially if they are protected against solar UV radiation and galactic cosmic radiation, long-time survival of spores inside meteorites is possible, and so the space environment is not an absolute barrier for natural transfer of life in the solar system. And so we can have such a kind of model that meteorites could be the transport vehicle for life. Of course, we need to study different processes. One is the escape process, and this is now possible. There is the existing theory says that especially by an impact of a very big meteorite, material is ejected to escape velocity, and there is a certain area at the rim of the crater, impact crater, the scalation zone, where the particles are also, the rocks that are ejected are not heated to very high temperature, and we are currently studying this in a simulation experiment in a DFG project. Then in space they are exposed to solar UV cosmic radiation, and I think this is the part I have shown you today, that it seems that there is possible that they can be protected against these environments. And then the landing process, this is something not so easy to study, but if there are good suggestions, it would be very interesting also maybe using the facilities. Andre Brack has developed the stone experiment for the biopan, where a meteorite or some minerals, rock material, is attached to the outside of the photon capsule, and they study how that changes during entrance in the atmosphere. So we call it now lithopanspermia. It's because it's not the single spores, but spores inside of rocks. And there are a lot of unanswered questions still, which have to be answered or can be studied, whether the spores can survive the ejection process. There are different approaches. Also the British group uses a gas gun and shooting, and we use a high velocity impact facility. The landing process, if there are good ideas, we think that one could study this with a photon facility. What are the most likely organisms to be expelled? We use always bacterial spores because they are resistant. But maybe those which live inside of rocks are much more interesting. And would they also survive? How can we think that they could have been protected against the space and the ejection process? And then there's a question of the long-term stability of the DNA, for instance. Spores are especially packed. They have the DNA especially packed between little proteins. But normal cells, do they survive so long? So more experiments are required in space and in ground-based facilities. And so I think from fiction we slowly come to real experiments by using the space station. Thank you.
Thank you, Vera. Questions, please?
What sort of kind of bothers me in these survival studies, of course this is a very important step to study whether the microbe can survive the travel, but it seems to me that would be also essential to then ask of whether it will survive the life or whether it would be able to get established. So I was thinking that the microbes, endospores or spores or whatever resistance structures can survive, for instance, in salt crystals for hundreds of millions of years.
Yeah.
Yes, but that's not exactly life. And even if it survives kind of in a potentially living condition, then when it lands, whether it will ever be able to establish life. Meaning whether its running would support replication. So the replication is still the critical requirement. This is sort of related to the earlier question, what Harry mentioned of pathogenicity of extremophores. And the answer to me seems to be that you cannot really transfer a microbe to a completely different environment because it's not adapted to it, and you at least would need to transfer the whole pig inoculum to have adequate survival rate and mutation rate and adaptation potency. So it may survive the travel, but not the life after.
I agree completely. We have taken only one piece of the whole scenario and have studied that first experimentally, because there were a lot of arguments that no microorganisms would survive in space, so the theory is absorbable. So we have taken that. But the next step really will be, how can we think if these kind of microorganisms land on a foreign planet, how would they then be feeling? How would they start growing? How will they adapt to that environment? And I don't think that space vacuum will favor any kind of metabolism of organisms. So it's really a tough vacuum, and you will only have resting organisms that can traverse through space. However, there are now some efforts, and I told you that we have a topical team by ESA that studies the response of organisms to Martian environment, that we now start to simulate Martian environments and see how microorganisms could adapt, could live or start living in a Martian environment on the surface or maybe in subsurface areas. And actually one of the facilities which we have now, is under construction to simulate the transport through space and then going into Martian conditions and see how they survive. Yeah, that's a very important question which has not yet been studied.
Yes. I want to answer from biologists regarding the survival of the DNA under the exposure that you have written in the last question. See, I was told that by people that what happens is when you are exposing the DNA to X-rays or any of the extreme the radiation, what happens is only the bonds break initially, and then once the source of radiation is removed, then it gets repaired automatically. Is it really true? I don't know whether biologists can answer.
Yeah. The radiation effect has two steps. One is the setting of the damage,
yes,
and the other one is the response of the organism.
Yes.
And that is, the setting of the damage is more a physical-chemical process.
Mm-hmm.
You first transfer the energy to the DNA, and then through chemical processes you break the DNA, or you make some cross-linking or different changes, chemical changes. And then the cell starts to detect this damage and to repair the damage, either linking breaks or cutting out pieces and replacing them by new. This all can only happen if you have real metabolism. So it cannot happen in a dormant state. Our spores have no metabolism at all. So they accumulate all the radiation damage. That's also one of the problems for dormant organisms traveling through space. They have normally in vacuum no active metabolism. And then you cannot repair. Normally you can repair. For instance, if you send the humans to Mars and they get radiation damage by the cosmic radiation, the cells are continuously detecting the damage and repairing the damage. Not all of them, but some of them. And but with our spores, they just accumulate the damage, and they start to repair and they germinate again and have cell growth.
No, if you remove the source of radiation, whether it can repair itself automatically, whether this spores, I don't know.
The spores only if they are
Whether
completely dry.
the metabolism can survive that kind of.
As when they start to germinate and grow again, then they can start repair processes. Not before. Before they are just.
No, what I'm saying is, suppose what you're saying is that microorganisms, once they are exposed to the radiation, they are really, they just accumulate the damage, nothing more. But what I'm saying is,
suppose you expose it to the radiation for, so let us say, several years, then bring it back to the earth and then you, whether it can survive, whether it can initiate life again.
Then they have a certain chance to survive depending on the efficiency of their repair processes. They start to repair, and depending on the amount of damage they have, they either can cope with the damage and repair it all so that they can survive, or the damage is so heavy that they can't survive. And normally it's an exponential survival curve depending on the dose.
So are there any measurements about this? What is the damage which can be survived? I mean, where under which it can survive? Is there any quantitative numbers for these things available?
Yeah, I think so. I mean, they did not simulate the transport processes, but there are numbers just from radiation experiments. I can even look.
Okay.
I can. We have written in the Relay review on molecular biology. We have written one on radiation effects in space, and I have to look at the data. I think we have to give it to you.
Yeah, Thorsten?
In light of your results, what do you think of the claim that the rate of microorganisms survive inside the camera that was on the surveyor spacecraft that landed on the moon? It was later picked up by Apollo.
This is with 99.9% likelihood a contamination after they have collected it either already in the Apollo module or in the laboratory. And they were, I mean, you know the story, and you told it, they were for 2.5 years on the moon, and then they collected pieces of the camera, and many pieces were cut into these pieces and were analyzed, and they all were sterile. Just one foam which they took out of the camera and put them in a nutrient medium showed them that there is at least one bacterium because there was a flow. But all other samples were sterile, and this organism was Streptococcus mitis, and this is a normal skin bacterium which lives on the human skin, and they found many of them on the astronaut skins and also on their normal clothes and so. And so, since they have collected the material and then they have put them in plastic bags with a zip, just close them with a zip, probably during this process there was a contamination. So that does not hold at the moment. And these are also normal vegetative cells which would not survive so long on the moon.
In your original samples, do you see a lot of mutants?
Mutants?
Have you analyzed the types of mutants?
Yeah, just by the vacuum exposure, the mutation rate is increased by a factor of 10. We look for different for metabolic mutations and also for poisonous resistance. And there is a Japanese group, Munakata, who also is in our has now experiment, and they have looked for the molecular specificity, and they have found that a special gene, a special part, special type of mutation is always somehow a certain group of bases together. It's very typical for the vacuum-induced mutation. So it seems that what we think that in vacuum, although the DNA is very well packed, there are some studies in the laboratory that the strands are separated. It's a reversible process, and that then somehow you find some kind of mutation. Just by vacuum. For UV radiation, I think we did not look, because you have always so much inactivation that you have not enough to look for mutations.
Maybe the few that survived would be something.
No, they were normal. So whenever we looked, they were all the same as the original. But you know, mutation rate is 10 to the minus 5, 10 to the minus 6. maybe increase the temporized force. So you need a lot of material to find the increase in attachment. So normally what is known from the laboratory, UV radiation and also cosmic radiation, do induce mutations. There are studies from the laboratory, not in the space experiment.
Okay, thanks, Gerda, again. We have now time for discussion. A few interesting topics have been brought up, like, for example, the issue of contamination, how that is, of course, important in future for any future claims that life does or does not exist on any body, astrophysical body or in space. This is one topic that could be discussed further upon. Does anybody want to suggest other topics at this point? Yes?
I would like to ask Caleb still
Yeah.
on a different factor which was not mentioned, and apparently you have not been looking at this in your exposure experiments, but of course on the space station, different people are looking at the adaptation to microgravity. So really, like living and metabolizing organisms, where it's apparently is very to some extent harmful for cellular organisms. But does that have any effect on microbes? Microgravity?
There are experiments which are at least 10 years old, where a French group on Daniel looked for antibiotic resistance of different bacteria. And you know, the problem is always with a space experiment, you need to have a lot of food controls, in-flight controls. So for all the biorec experiments and the European experiments, we always have a 1G control. It's a slow rotating centrifuge which simulates 1G in space and microgravity. And using this and ground controls, they found that the antibiotic resistance of the bacteria, don't ask me what kind of bacteria, different kinds, probably some more, maybe E. coli or something like that, that they have an increased antibiotic resistance. And these are the main experiments which I know with bacteria. Then there were some experiments looking for the horizontal gene transfer, more or less, the processes of DNA transport through membranes, conjugation, transduction, and transfection. These processes, either transport of DNA by bacteriophages or just from one cell to the other. And as far as I remember, there was no effect by microgravity. So at the cellular level, there is not, at the bacterial level, it's not very much. At the cellular level, in human cells or mammalian cells, there were found a lot of different changes in signal transduction and gene expression. And especially in the immune system, in leukocytes, it seems that they are somehow disturbed. That's work by Kogli or Mr. Kogli. We were interested in whether the response to radiation would be changed in microgravity environment. So we had irrigated samples before the mission, because the cosmic radiation is not intense enough for such an experiment. We have irrigated them before the mission, kept them frozen, and then brought them to space and allowed them, when they were in space, to respond to the radiation and start the repair processes. We did that in human cells and in bacteria, and we found that the repair processes and the kinetics and efficiency of repair was not changed in the microgravity environment. So it's very difficult with microgravity experiments because it's not like in the laboratory where you can repeat it and repeat it and repeat it until you have it confirmed. You have one experiment, and the handling and everything, you have to bring them, for instance, in frozen state. And then you have to grow them. So you have to have some cryogen or so with them and so. So everything is not so elegant like in the laboratory still. And it will be further on. Because we will not have astronauts to do the work. Due to the core complete decision of NASA, we will have not more than 3 astronauts on board, and they cannot do the work, the experimental work, the scientific work. They must take care of the space station. So it's a really problem with the whole space station. Doing real laboratory work, it's not the idea was once that the scientist takes his suitcase and goes to the lab, to space and does the experiment, but that is not yet reality. I think in our astrobiology book there was one of the paragraphs is light and gravity, where people have written what so far has been done with space on microgravity.
Regarding the importance of metabolism, is there a possibility to imagine some sort of metabolism on meteorites, for example, or comets rather, which would require, ideally, of course, liquid water, which we don't have, but possibly other unexplored ways of metabolism, which could be possible in comets. I mean, are there possibilities which have been mentioned in the literature so far?
You can have solid liquid water inside.
Sorry?
You can have solid liquid water inside comets. Sort of very soft ice, which is almost water can have many phases, which is almost a good degree of non-experience.
So why is it liquid? I mean, the temperature should be around.
Yeah, because the pressure. No ice.
Yes.
Constant pressure.
Yeah.
So if your comet core is big enough,
Right.
it's
Yes.
slightly more into the
Okay. So, what do you think, or other people think? Is that a possibility to have, perhaps, to allow perhaps metabolism or sustain life otherwise? In an active form rather than a dormant way on comets. You don't.
I have the difficulties to imagine how this stuff could come into comet.
Yeah, right. But I mean, that's another question. I mean, many things are difficult to imagine at this point. But you have been exploring one particular route or one particular element of panspermia. And now the issue of panspermia is probably a rather broad one. It's probably also not out of the world with your work. It will come back. So the question is, what are possibilities of? What are possible pathways to revive panspermia again? I mean, it will probably come up again in the literature. And so you could then look at this element. If it was there, if some sort of life, this metabolism was active in a comet, regardless of how it got into there, would at least any kind of metabolism be conceivable?
The question which I want to ask is whether the process of metabolism, how much is damaged by radiation? Whether metabolism, is there any investigation of the process of metabolism itself to the radiation damage?
I think that it will not come directly close to Jupiter or so when you have a very high radiation dose. Normally in interplanetary space, the radiation dose is not damaging the bacterial cell. It's damaging humans, maybe, but not a bacterial cell. They tolerate 5,000 gray, which is without being killed. So that's not a problem. So radiation is not a problem for the metabolism, especially if you have a cell that metabolizes and can then cope with the damage. So assuming you have your comet And inside you have liquid water. And it travels through space. And it's sometimes cold, and then it becomes maybe a little bit warmer when it comes closer to the sun. You have salts inside, you have liquid water. What kind of energy source? Chemical energy source.
Yeah.
Why not?
No, but is there any actual measurement of the, what is that maximum dosage which can be served, under which the metabolism can survive? Is there any measurement, laboratory measurement of the...
There are very little data on low dose exposure of cells for a long, long time, because nobody was so interested. We don't get real damage, so it's very difficult to find something. But it's
No, but see, you are mentioning about the Jupiter, that's the reason I'm asking you, whether we can subject a living organism to very high dosage of this one and see whether the metabolism still survives. Is it a global experiment?
you have to let them just grow under a continuous low dose field, radiation field. I think there's little done. I know that somebody has done it for yeast cells, but it's not really published. So it's not very much done in that field. Now, what do you do with the rats?
What is the reason why it is not done? Why is it not? Is it not interesting of the experiment? Why is it not pursued very vigorously? Is there any reason why this experiment is not pursued very vigorously? Is there any?
I think in radiation biology, normally you wanted to measure the effects of radiation. And in order to have visible effects, you need to have high doses and then a real dose response curve. So whatever you have as an effect you measure, you want to have it as a function of the dose increasing or decreasing. And if you have, but what you want to measure is no effect. So what level can I irritate with no effect? And so far people are not so much interested. Probably.
Is it possible to conclude then the metabolism is not affected by radiation? Can we say that? That's what I am asking you. Metabolic processes are not affected by intense radiation. Can we make a statement?
I mean, metabolic process is a big word for many, many different steps. So you have
let's say replication.
to take exemplarity, one kind of metabolic step, or one kind of gene expression, or one kind of something you have to do, but that you can do. What do you think?
I think in quite many surroundings, organisms tolerate certain levels of radiation. In Chernobyl, there is a whole lot of ecosystem growing around the radiating reactors, or even inside nuclear reactors, there's the radioactive elements growing quite happily. So metabolism tolerates it, and it can benefit at least the radioactive.
So essentially, metabolism, radiation doesn't have any effect on the metabolism. Can we make the statement? I want a quantitative statement. I don't want a general kind of thing. I want to know whether is it possible to have a...
But too much of anything is bad.
I think that the essential thing is still that life seems to be some kind of feedback, very strongly feedback loop system. And that means that when you do any kind of modifications to the environment, then life adjusts itself to this environment, whatever it is. Then the matter is really room for these extremes. So that is why I think that it's very hard to, it's completely nonlinear.
Yes, but then I think what you really want to ask is perhaps when does this process no longer work at all? That is, it's not a question of when is there no effect, but when does the effect of radiation really become too strong that there's no life at all? Is there no upper maximum to your radiation response curve?
I have to be more specific because metabolism is a big word. I have to be more specific, saying, so which exactly part are you thinking of?
I think I'm really...
It's a question because it's too topic. You have to ask a more specific question. It's not a lesson.
No, but if it is true that the life adjusts to any amount, the environment will just adjust itself. Whether it doesn't get amount to the same thing, saying that any damage is immediately repaired.
But
Isn't it? That's what you are saying, isn't it? That's what essentially what you are saying is life adjusts itself to any extreme surroundings kind of thing.
Not any, but to some. Life always adjusts to optimize situation to prevent situation.
But the problem is that how long do you expect this process to take place? Because then you have to take into account that at sufficiently long times you will be flash sterilized a couple of times by bears from the sun. I mean, they grow up by yeah, but if you take sufficiently long time, then the magnitude of the flash goes up dramatically.
May I add something? I think we are too much looking at this one cell that is metabolized. And already in the extent we need a more inoculant usage like defects and so I think the question might be much more what are the minimal requirements to sustain an active ecosystem? Because normally you have always one is metabolizing this substance, the other is using this one, so you have somehow cycles and interaction.
Yeah, right.
And I think a single cell doesn't help us very much. We need this ecosystem.
I think I would even start in the other way and say that what kind of chemical structure would be essential to serve as some kind of basic building block by which you could create life essentially by adding water, for instance. So what kind of structure you would probably need some kind of cell membrane or some kind of stand-in for this kind of membrane system, and not very much more, and then suitable ingredients. And so what would be the building block required in this way? And then we end up in a very interesting thing that what happens, for instance, in the cometary environment where we have all these building blocks available, we have radiation which modifies this continuously. We have low gravity, which means that we can really build these fluffy structures in an easy way. So what else is required? So is the best recipe still for forming life to take a comet, dip it in the ocean and wait 1 million years or 10 million years? So is this still this mechanism? So can it be formed, so can life really be formed from a chemical basis really this way? And then there's an evolutionary process continuing.
Well, we really don't know today of how did it start, although apparently it did start relatively quickly, but we don't know how it happens. Very fluently or whether it is very statistically unclear. But the comments have been postulated as scientific origin of life side. So it might be a good condition to
no, because the laboratory is too small. If you take a comet size 30 kilometers cubed and splash it here, then you have all the temperatures, you have all density gradients, you have everything available in one go. So there will always be some kind of optimum environment where you can create this. You also have all these
but don't you have evidence already from the fossil things and the Pacific vents? They have seen the living organisms in around 3.8 billion years ago when there was an intense irradiation of the cometary bombardment of the Earth. And we have seen in the fossil we have been dated, and we have seen life forms at that time. So doesn't it support the argument that the cometary life comet has brought life to the Earth? This does not mean that the terrestrial life is not there or not. I am talking about purely from the point of view of we know that there is during the 3.8 billion years ago, before the present, there was an intense comet bombardment of the Earth. This is something which astronomically we know. And then we have fossils, which is dated to be around the same time, and they seem to have life forms. I mean, it has been seen in the fossils in the Pacific vents, South Pacific thing. Yes, I think from 10 years ago this has been unearthed and the evidence is found. And doesn't it say that whether the life existed in the Earth before or not? I am not talking about that. I am talking whether the original life started with the comet. I am not asking about that. I am talking about purely from this point of view. Can't we say definitely the cometary life forms exist in the comets? Isn't it possible to conclude from the fossil evidence? That's what I am saying. I am asking whether it's not possible.
No.
Why? What is the reason?
Well, you have to wait a couple of hours.
You have one more comment?
Yes, it is direct continuation to
the audience.
to the question of minimal metabolism, and this requires that we first define what we mean by metabolism. For instance, to make a difference between reactionism and metabolism. What is simply a reaction and what is a metabolic? Of course, metabolism is chemical reaction, but still we need a precise definition, as we do require for the notion of life and virus, and then what we call real life, membrane life. So I would propose here a principle of systems thinking, which I will be speaking, I guess, after the coffee is yeah. So what is a system? It is something which has something inside it, and its environment. That is the basic idea, nothing more. And this is a very simple principle, first principle of system thinking and system theory. So, metabolism and reaction. We have here the same question. And we can apply the notions of exo and endo. So we can speak of exometabolism and endometabolism. Exo and endo, this distinction is very common in biology, because biology is all about systems, and very complex systems. And evolution goes from exo to endo. That's a principle of evolution. So we have exometabolism. It is something which has no intestine. It is on the skin. Well, of course, intestine is also skin, but it has only extra skin. So that is exometabolism. And then you have, this is viruses. Viruses have exometabolism. They directly react with the environment. If the conditions are appropriate and favorable for, they can exchange matter and energy and build up offspring. That's all they have. Their function. Okay, so we have these two notions, and now we come to the theme of the paper, comets and comet metabolism, or primitive life form on comets. Certainly, I think we can realistically think that exometabolic life can exist on comets. If it can exist in the Lake Vostok, why not in still colder temperatures?
And the response so far seems to be yes from some of the audience so far, right?
And once the comet comes to near solar orbit, on its orbit, so the ice can melt and it can create favorable conditions for the virus to
to metabolize, to begin to metabolize, as they do in cell. Well, that is, of course, that is space environment.
Yeah, that's the idea now so far. The question is only what would be then the real scientific proof that this really works. And I mean, Gerda has been doing work on trying to establish how life can actually survive, and that particular question answered, or this particular issue does not answer, of course, the issue that we need to address in order to prove that there can be some life form be sustained in a space environment. Because, I mean, the main difference, of course, is that you're talking about a habitable environment, somewhat habitable environment sustained by the comet. I guess in order to address the issue further, one probably needs to think of these kind of environments in the future and check whether in such environments whether one can build them artificially or however, whether one could do these kinds of experiments where some sort of metabolism and perhaps some collective life, of course, as you mentioned, the importance of this, can be studied. So maybe that would be the next level of investigation on towards the big issue of panspermia.
But comets and nuclei is probably not in the thermal equilibrium. I mean, all the heating will take place on the surface, and that surface will disappear when it approaches the sun, so you don't have the environment to create anything.
But you don't. I mean, not all the comets, of course, to go close by to the sun.
No, but I mean, in order to heat it up, in order to have liquid water, you need to get very close to the sun.
Can you just do it by pressure? I mean, you pressure ice gets not liquid, but it gets soft.
But the cell compression, even in 30 kilometers, is not that high.
I mean, how liquid is this water have to be?
I mean, you have to go even to several hundred kilometers just to form the ice, to make it semi-fluid.
There's some interesting details to this alkalic prokaryotic chemistry, which is, for instance, that RNA nucleotide polymerization drives better in ice, like between ice crystals. So in the liquid phase between ice crystals. So ice accumulates polymerization of RNA nucleotide, also RNA nucleation. So in this sense, the ice would be kind of favorable, at least for this step of the process. But then other steps, of course, would require liquid.
You want to comment here?
Can there be any kind of chemical heating, like polyvinyl? Because there is these polyvinyl and like white heater in the bottom of the sea. Polyvinyl heats water and everything like that. Can there be any kind of chemical heating?
No, I would start to argue in a different direction. The fact of life is that we have these few flybys. So we have the flyby of Halley, and then we have a few other comets, and Stardust now in January this year. And they all show this very strong existence of long polymerized changes of molecules. And this two comet, which we now flew by in January, that shows no organics at all. So we have just these long polymerized organics in. So the fact of life is then that we do have complex molecules formed directly here, and they are quite abundant around these bodies. So that is some kind of solid ground we have to stand on now. So then the other question is that how much do we like or want to construct living entities on the surface of this? I would be quite skeptical to having any kind of life on this comet because the erosion is quite strong. So AB2 is something which dropped into the inner part of the solar system this last century. So it's a fresh comet from that point of view. And the erosion is of the order of say 4 or 5 meters per time cycle. So we really skim off the surface from the comet to a huge depth. So I would rather go then and think along lines that it's a chemical thing. We are building by the cosmic radiation bombardment some kind of complex structures. We are building long molecule chains, and these then can be built as raw material for life in a different environment.
That would be on Earth then, or what?
Yeah, that would be on Earth or some place where we melt the whole planet or something.
There's some observations of complex molecules in space. My question now is, if our Earth, which of course has life, was exploded, or by, for example, our sun getting older and older, and everything would be somehow killed, first of all, but then spilled into space. How would an outside observer see that? Would an outside observer see any traces of complex molecules from our solar system? What do you think? Okay, no answer. Right, so I think that was a good start. We had some lively discussions here, and we resume after half an hour coffee break with the talk by Seppo. Natalia, Natalia Gonzaleva will not be because she didn't manage to get a visa in time. So we have 2 talks in the afternoon. The second one is by Lund. Okay, so the coffee I believe is just outside here.